In this video, we are going to talk about properties of Fourier transform. This is our overview slide, which we'll spend less than 5 minutes on before we go over these properties in more detail and with more examples. First, we're going to start with the review of the Fourier transform, the formulas, and then we're going to start with a function f of t, given its Fourier transform is f of omega, and then a function g of t whose Fourier transform is capital G of omega, and we're going to look at these 7 properties. This first one is delay. So how does the Fourier transform change? If we know that f of t is this Fourier capital F of omega, then f of t minus t naught, in other words, we delay our time by t naught, then our Fourier transform changes into e to the I omega t naught times f of omega. What is tempting but is not true is the Fourier transform of f of t minus t naught. It is not equal to the Fourier transform of f of t minus the Fourier transform of t naught. Instead, this is what the Fourier transform becomes. So we're going to look at these 5, 6, 7 different variations on Fourier transforms and how our answer may not be what we initially expect. To quickly review the Fourier transform, what that did, it allowed us to look at a function f of t that may not be periodic, but then analyze it very similar to how we did the Fourier series for other functions and write our f of t in terms of this e to the I omega t, which translates to sines and cosines. And this is the formula that we have for non-periodic functions. This inner part here is called the Fourier transform. And what it does is it takes a function f of t, multiplies it by e to the I omega t, does this integral, and this integral essentially integrates out the t, the time variable, from this function, so that we're left with the function of the frequency omega. So it's a transformation of a function from where t is our variable, time is our variable, to a function where omega, frequency, is our variable. Or in other words, we go from the time domain to the frequency domain. Then what we can do with this function, this Fourier transform, is plug it back into this outer function f of t, and what we get is a function, then our original function in terms of our sines and cosines, or I omega t. It is true that the Fourier transform is linear. In other words, if you multiply a function f of t by c and then take the Fourier transform, you can pull out the c, the constant, so that this is equal to c times the Fourier transform of f of t. Also, if you had the Fourier transform of f of t plus another function f of t, you can separate out the addition so that it becomes the Fourier transform of f of t plus Fourier transform of g of t. Linearity, however, does not help us with things like f of a function of t times another function of t, unless this function of t is a constant. But if it's a full-on function of t, in general, we cannot do this separation of pulling this out. It does not become the Fourier transform of f times g of t does not equal to the Fourier transform of f times the Fourier transform of g. And in fact, what we will see is the Fourier transform of a function f of t times a function g of t is equal to 1 over square root of 2 pi, the convolution of f with g, and we'll define convolution later in this video. So this video is about properties that might be unexpected from Fourier transforms. And we're going to start with the idea that we have a function f of t whose Fourier transform is capital F of omega, and we have a function g of t whose Fourier transform is capital G of omega. So again, the double arrow indicates a Fourier transform and its reverse process. And we'll look at these 7 different variations on the Fourier transform. We will start with delay. The idea here is the properties of Fourier transform. We know the Fourier transform of f of t, and we know the Fourier transform of g of t, although in this case for delay, we don't care about g of t. But we know the Fourier transform of f of t. So how does a delay, in other words, if we do t minus t naught, how does that affect our Fourier transform? It would be super convenient if the Fourier transform of f of t minus t naught was equal to the f of Fourier transform of f of t minus Fourier transform of f of t naught. But it's not. It's equal to this here. And so let's derive this formula here. And we'll start with the definition of the Fourier transform here. So Fourier transform of f of t minus t naught is equal to 1 over 2 pi integral from negative infinity to infinity dt. Our f of t, now we have f of t minus t naught, and our e to the I minus I omega t. We really do want to integrate a function over a variable, so we're going to replace this t minus t naught with alpha. So if alpha is equal to t minus t naught, then t is equal to alpha plus t naught, which means dt is equal to d alpha. So what we have then, our integral gets converted to 1 over 2 pi integral d alpha, that's the dt, e to the minus omega, and then our t is converted to alpha plus t naught, and then f of alpha. Here I manipulated my exponent so that I can break this up into e to the minus I omega alpha and e to the minus I omega t naught. This here now is a constant that I can pull out. And now the only thing to notice, see, this actually isn't too bad, is this part here is just the Fourier transform of f of alpha. So what we have is our final formula. The Fourier transform of f of t minus t naught is equal to e to the I omega t naught times our Fourier transform of our original function f of t. The next property we will look at is time inversion of a real function. So we know the Fourier transform of f of t. What is the Fourier transform of f of negative t? So here's my f of negative t. We plug that into our Fourier formula, and that's 1 over 2 pi integral dt e to the I omega, negative I omega t, f of negative t. Since we usually don't integrate f of negative t, but something of the form like f of t, we're going to make a substitution for alpha equals negative t. That way we plug in when we get f of alpha, which is more normal. So if alpha is equal to negative t, then t is equal to negative alpha, and dt is equal to negative dA. So let's look and see how this changes our formula. We have, we'll get to this negative sign in a minute, but we have 1 over 2 pi integral. Now, if t over here, if negative t is negative alpha, infinity, so if negative t goes from negative infinity to infinity, that means alpha, which is negative t, will go from infinity to negative infinity. Then we have our dt, which is negative dA. So we have dA here, or d alpha here, and here is where we pull out our extra negative sign. E to the I omega, and this is a negative alpha, so that becomes positive here. So we have alpha, f of alpha. And just because it's a little weird to go from infinity to negative infinity, I'm going to change this back to negative infinity to infinity, but then this sign here is going to go from negative to positive. Now, this almost looks exactly like our Fourier formula, right? We have our 1 over square root of 2 pi, our integral, negative infinity to infinity, d alpha, this is d tau, but that's all right. E to the this is just e to the positive I omega alpha, and then our f of alpha. So it looks exactly the same, except instead of tau being our variable of integration, alpha is our variable of integration, and then there's no negative sign here. However, if f of t is pure real, then I omega alpha is going to equal to negative I omega alpha, which means this is the complex conjugate of the Fourier transform. I am going to skip the derivation for the even and odd functions as well as spectra for pure real, but I am going to do this transformation. If we know the Fourier transform of f of t, how does that relate to the Fourier transform of the derivative of f of t. And just a note, we're going to use this fact over here. Without it, we can't finish this, we can't come up with this property here. And this looks kind of frightening, but it's not. So we're going to take the Fourier transform of df dt. We're going to plug in df dt into our Fourier transform formula, which is 1 over square root of 2 pi, the integral dt e to the minus I omega t df dt. And to integrate, we're going to integrate by parts. We're going to let u equal to e to the minus I omega t. That means du is I omega, negative I omega e to the minus I omega t. We're going to let v prime equal to df dt, which means that v is equal to f of t. Plugging into our formula here, so first we're going to put the constant 1 over square root of 2 pi, and then we need u times v, so u is e to the minus I omega t, times v, which is f of t. We're going to evaluate that at negative infinity to infinity, plus, again, pulling out our 1 over square root of 2 pi. Then we have our integral of v, which is f of t, times u prime of t. Here's u prime of t. We're going to take out our constant I omega, which is over here, e to the minus I omega t. And this negative here cancels with this negative when we subtract the integral, and that becomes a plus. And this is where we use this fact over here, which I barely noticed except that I was stuck. We're going to use the fact that f of t approaches 0 as t approaches infinity or negative infinity. And this is true for any function f of t with a valid Fourier transform. So this is kind of important to remember. But that means this whole part over here goes to 0, right? So f of t approaches 0 as t approaches infinity and negative infinity. Here we don't have f of t, but we have the integral involving f of t. So we can't just make that go to 0 either. But this is exactly the Fourier transform. So what we get is I omega the Fourier transform. So this is how this is related. If we know the Fourier transform of f of t is equal to capital F of omega, then the Fourier transform of the derivative of f of t is I omega capital F of omega. The next property we're going to cover concerns the multiplication of two functions f of t and g of t. If we know the Fourier transform of f of t is capital F of omega, and we know the Fourier transform of g of t is equal to this capital G of omega, then we want to know the Fourier transform of f times g. And the solution to that is going to involve this new operation called convolution, which we will discuss. Next, we're going to talk about the transforms of the product and convolution of two functions. Convolution you may or may not recall from differential equations, but that's mostly what we're going to discuss is a review of convolutions. So convolution is a special type of multiplication, and its symbol is this multiplication sign with the circle. The circle just to tell us, yes, it's multiplication, but it's not our normal multiplication. So when we take the convolution of two functions, g of w and f of w, it's equal to the negative in not the negative integral, it's the integral from negative infinity to infinity of dw prime. This prime doesn't mean derivative, by the way. It's like the other w, not this w, but the other w. So it's our w prime is our variable of integration times gw prime times f w minus w prime. So we'll look at this closer. But the idea is now, if you take the transform of the product of two functions, so the Fourier transform of f of t, g of t, which I'm going to just write over here, Fourier transform f of t, g of t, it should come as no surprise that it's not equal to the Fourier transform of f of t times the Fourier transform of g of t. That would be convenient, but it is not the case. I do want to point out that it is true the Fourier transform is linear. So if you have the Fourier transform of f of t times a constant, you could pull the constant out. Or if you had the Fourier transform of f of t plus another function g of t, you could separate out the two Fourier transforms. But linearity, it does not help us with the Fourier transform of the product of two functions. But what we do have is the Fourier transform of the product of two functions is equal to 1 over square root of 2 pi Fourier transform of f convoluted with the Fourier transform of g. So this is the convolution. So multiplication in the time domain is convolution in the frequency domain. Similarly, if you take the Fourier transform of a convolution, then that would just be the multiplication of the two Fourier transforms. In the case of this convolution and this product, I am not going to derive these formulas as I have for the other properties, but what I will do is focus on how to calculate the convolution of two functions. The example I'm going to consider is the convolution of f of t, which is a square pulse over here, and of g of t, a rectangular pulse. I've written now my h of t is going to be my convolution of with f of t with g of t, writing that in terms of my convolution formula, negative infinity to infinity d tau. Tau is probably a better variable than this omega prime because, I don't know, omega prime looks like a derivative to me. So f of tau, g t minus tau, which, by the way, it doesn't matter which one you make equal to t minus tau. You could make f of t minus tau and then put g as tau. But anyway, let's look at g, our function g, as being the t minus tau. These are my two waves, my square and my triangular pulse. So what happens when we make, instead of going g of tau, we go g of negative tau? Well, that's a reflection across this vertical axis. So we just kind of reflect it across. And then when we have added t to it, this lowercase t, so t minus tau, we're going to shift our g of negative tau to the right by t units. So here, if t is equal to 2, this point here comes out to 2 instead of staying at 0. Similarly, all these other points get pulled over, shifted over by 2 units, and so the whole graph shifts over. Now when we look at this integral, we can interpret this integral now as the area under the product of f of tau and g of t minus tau. And I also want to point out the area under the product of f of t and g of t minus tau depends on how much we've shifted our curve g over. In other words, what our value of t is here. Here t is equal to 2, here t is equal to 0. So how much we shift will impact the area under the curve. And I'll show you why that is in just a minute. But since it depends on that, we should note that the convolution of f of t convoluted with g of t gives us a function dependent on t, the amount we have shifted. Before we move on, I'm going to go ahead and get rid of these notes over here because I don't think we need them in our discussion of convolution. So I moved everything up. So over here I say product of f and g. When we take the Fourier, we need to do the convolution. I have my h of t, which is defined as my convolution of f of t and g of t over here, plugged into my convolution formula. And then I also said it doesn't matter which one gets the t minus tau versus tau. Here f has the t minus tau. Here g has the t minus tau. And we said that this integral could be interpreted as the area under the product of f of tau and g of tau. Also something to note, now our h of t is now shifting our graph. So let's look here. This is our picture when t equals 0, and you can see there is no overlap of our triangle wave with our square wave here. And you can also see when there's no overlap that the product of g of t minus tau and f of t will equal to 0, because whenever g of t is non-zero, that's in this region, f of t, right, this is the black function, is equal to 0. And over here, when f of t is non-zero, g of t minus tau, has gone to 0. So their product is 0 when there's no overlap. Sorry, I had to stop my recording because there was this huge helicopter or something that came overhead. I don't know if you heard it or not. But anyway, so when there's no overlap, our product is 0. And our h of t now, in some ways, measures how much overlap there is between f of t and g of t for a given value of t, remember. As we move t, we'll see more and more overlap. And as we see overlap, we'll start to be able to get non-zero products of g, t minus tau, and f of t. But I'm going to show you some pictures of that right now. So as I was saying, here is our t equals 0, but our h of t, we need to consider all the different values of t. So what that's going to do is it's going to move this triangle wave over from negative infinity to infinity. And we're going to be looking at, as it moves across, what the area under the product of f of t and g of t minus tau become. Now if you look for t equals negative infinity, something displaced way out over here, all the way up to t equals 1, there's no overlap. And whenever f of t has non-zero values, g of t has come down to 0. So the product will be equal to 0, and therefore the integral is equal to 0. Now you can see as I move g of t, where t goes from 1 to 2, there starts to be some areas where now f of t is greater than 0 and g of t is greater than 0. We're going to focus now on this interval, t from 1 to 2, where the base of the square wave is partially overlapped by the triangle wave, where the complete overlap is at t equals 2. That's right over here. But remember, if we're kind of between 1 and 2, there are times, oops, can't get this to move, where the whole base is not eclipsed. So over here, in this value of t, right, f of t is non-zero, but g of t is 0. And then when we get over to 1, that's when we just start at 1, right? They're both equal to 0, but then right as we get to the right of 1 and the left of 2, then there is some overlap. Now we can start looking at our product of f of t and g of t minus tau when we're t is between 1 and 2. So we know, and fortunately, we can do that multiplication easy because f of tau is equal to 2, right? The height is equal to 2. So 2 times g of t. Over here at t equals 1, then basically we're going to double the height, so something around here. And then by the time we get to this endpoint, g of t is 0, so we double it, but we still get 0. So we're adding up all of our area right here, sort of this triangular area. And remember, if we're only halfway, in other words, if g of t is not at 1, it's not at 2, but it's at 1/2, so right over here, then we're going, again, this gets doubled. This is over at 0, so we're only going up to, from t equals 1 to whatever value we're at, 1/2, t equals 1/2. So we can plug all that in now. My h of t, my convolution, is equal to the integral from 1 to t d tau, f of tau, g t minus tau. F of t is equal to 2. G of t minus tau is 2/5 t minus tau. And I have this because g of t minus tau is just a line, right? It's a line. Its slope is 2/5, and then t minus tau is my variable. And then I can multiply, I can integrate with respect to tau, plug in my limits of integration, and this is my formula for h of t when t is between 1 and 2. Now we're just going to look when we start at t equals 2 when there's no more overlap of the entire base of this square wave. So we can move our g of t, we're going to keep going. There's no overlap until we reach, and I guess the scale, it's off the little graph here, but until we reach t equals 6. So the idea again is between t equals 2 to 6, the entire base of the square wave is totally overlapped by the triangle. Here I've illustrated with t equals 3. So here t is equal to 3, it's shifted over. we're going to do the product. So f of tau, again, is just equal to 2. Its height is 2. So 2 times whatever g of t is. So I'm just going to double this height over here, which I'm just going to approximate on my graph to be here. Doubling this height over here, approximating on my graph. I'm just going to approximate it to be here. So I'm going to add up all these heights from one end to the other. I guess I need to go a little higher. And we're going to integrate over the entire base of this square, t equals 1 to t equals 2, because the entire base of this square wave is being overlapped by the triangle. Here we moved out t equals 4, and you can see the area we're integrating this, approximating twice g of t will be up here, twice this value is around 1, so we're integrating this yellow area. Again, we're integrating for t goes from 1 to 2. Here we're out at t equals 5, and our area, again, twice g of t, so maybe somewhere here, twice of this is a little more than 2. So we're integrating this area here, and again, we're going from 1 to 2. Now, at t equals 6, we have, we're going to have all this area here. And you notice at t equals 6, this is our maximum area. And the reason why it's maximum, remember I told you h of t in some ways is a measure of overlap. And so what that means is we're comparing our g of t, shifting it over to see when it looks most like this square wave and most in phase with this square wave. So that's where this portion here of this triangle wave looks most like the square wave, and again is also most in phase with this square wave. So that's kind of what h of t is measuring. It's sort of picking out the pattern of f of t. It's like it's moving g of t along and then giving you a measure of how much in phase and how much the shapes match. And now we can write our formula for h of t. For this whole interval, since there's always overlap over the entire base, we're going to integrate from 1 to 2 d tau f of tau g minus t minus tau. So our f of tau is 2, g of t minus tau is 2/5 t minus tau. We multiply 2 times 2, and then we integrate, plug in our limits of integration, some arithmetic, and we get 4/5 t minus 6/5. And again, this is for t between 2 and 6. And one thing to note, here in this interval, we integrate from 1 to 2 because there's always an entire overlap between t equals 1 to 2. Previously, before, when we were looking between t equals 1 and 2, our overlap may have just gone from 1 to, in this case, t equals 1/4. And over here, there's no overlap in that where there's non-zero. In other words, here, g of t is equal to 0, so the product is equal to 0. So we're not going to integrate over the whole range from 1 to 2, but just up to t. That's why we had to separate t from 1 to 2 separate to give a different formula than t equals 2 to 6. When we get to t greater than 7, you can see now we're back to the original case that when g of t minus 0 is not equal to 0, then f of t is equal to 0. And vice versa, when f of t is not equal to 0, then g of t minus tau is equal to 0. So the product is equal to 0 and the integral is equal to 0. And of course, this is true for anything t greater than 6, and I just showed you 8. To summarize, our convolution of f with t gives us a function h of t. For t between 1 and 2, h of t is equal to the integral from 1 to t. And we only go from 1 to t because at this point beyond t, g of t minus tau is equal to 0. So it does not contribute. So we only integrate from 1 to t, f of tau g minus t minus tau. F of t is 2, g of t minus tau is the line 2/5 t minus tau, and we get our function for h of t. When t is between 2 and 6, we have a different function. We're going to integrate along the entire base because at this point, the entire base of the square overlaps with non-zero values of g of t minus tau. So we're integrating from 1 to 2, the entire base of the square, f of tau, which is equal to 2, and g of t minus tau, which is 2/5 t minus tau. Integrating with respect to tau, we finally get our h of t is equal to 4/5 t minus 6/5 for t between 2 and 6. All other values of t are h of t, our convolution, equals 0. The last function we'll look briefly at is correlation. Like convolution, I'm not going to derive how we get the Fourier transform, but I'm going to say this formula here is defined as the correlation between a function f and a function g. And when we want to take the Fourier transform of this correlation function, that's the square root of 2 pi, the Fourier transform of f, times the Fourier transform of g to the minus omega. Looking here at the formula for correlation, it's really quite similar to the formula for the convolution. Here I have my convolution formula for reference. So our f of tau, it's an integral d tau, our f of tau, and then looking at our g tau minus t, now we have t minus tau. So the first thing we're going to say is this takes g of t and it leaves it as g of t, whereas over here we inverted g of t and made it negative g of t. And then, here we're shifting by t, here we're shifting by t as well, except in the other direction. So in other words, it's very similar to convolution. The whole idea of correlation is similar to convolution, except that you don't invert. You do not invert our g of t. And also like convolution, correlation is a measure of the similarity of the two signals. To review what we've discussed in this video, we talked about properties of Fourier transform. We reviewed the Fourier transform formula, which is right here, and then we assumed we had a function f of t, and we knew the Fourier transform is f omega, this capital F omega, and we have a function g of t, and we know its Fourier transform is capital G omega. Then we looked at what happens to the Fourier transform of f of t when we delay our signal t by t naught. In other words, f of t minus t naught. And we see that it's related to our original capital F of omega, except now we need to multiply by e to the minus I omega t naught. We looked at time inversion of a real function. We looked at even and we talked about, or we reviewed the formula for even and odd function. We reviewed the formula for spectra for pure real. We derived the formula for, if we know f of t, what would the Fourier transform of the derivative of f of t be? And it would just be I omega f of w. And then we talked about transforms of the product of two functions. And we said that if we had the product of two functions, its Fourier transform of the product would equal to 1 over square root of 2 pi Fourier transform of omega convoluted, not just multiplied, but the special multiplication convoluted with g of omega. And convolution was defined here, and we spent quite a bit of time talking about the convolution integral here. And we did a very brief look at correlation. It was very similar to convolution without the inversion of our tau. And that's it for this video. Thank you for watching.